everyone. So today we will talk about exercise 5.51, beads on a hoop. So this question is about a hoop on which there are two beads of mass small m, and the hoop itself is big M. And these two beads are originally at the top, and they're given tiny kicks so that they slide down, and one slide to the left, the other to the right. And the question is asking us the largest value of small m over big M for which the hoop never rises up off the ground. Now, how can we solve this problem? Well, first let's try to analyze the forces here a bit. Let's look at the individual beads and see what forces these beads experience. Well, first it experiences a normal force. This normal force is given by the hoop. And there's also a gravitational force. And so then what is the reactive force on the loop itself? Let's look at the hoop. For the hoop, because it provides this normal force to the two beads, it also experiences the two reactive forces of these two normal forces. So they look like this. And the loop itself also experiences a gravitational force downwards. And the net force equation gives the 2ny, the y component of the two normal forces, must equals to g, so such that must be smaller or equals to the gravitational force, such that this loop stays on the ground. And so now our job is just to find how big can this n be, so that's always smaller than g. And so now let's try to do that. So first, in order to find n, let's look at these beads again. Let's try to analyze the beads. So for the beads, it's going around the loop, and so there must be a centripetal force, which is mv squared over r. And who provides the centripetal force? Well, normal force provides the centripetal force, as well as a component of gravity, and that component is plus g cosine theta. Why? Well, let's look at this loop again. So if you have a loop, let's say b is originally here, now it's here. Let's call this theta. And so gravity is downwards g, and then this is theta. And then if this is theta, let's look at g. So g, we said if this is g, this is the tangential component of gravity, and this is the radial component of gravity. And so then, if this was theta, this is a right angle, and this is a right angle. This is 90 minus theta, and so this must be theta. And the reason why this and this is a 90 degrees angle is because we have a radius. So remember, this is a radius, and we have a tangent line, and their angle is always 90 degrees. And so that's why this angle is 90 minus theta, and so this is theta. And so it's m plus g cosine theta equals to mv squared over r. Next, let's try to find v. What can v be? Once we get v, we'll be able to get n. And get n, we can get the y component of the normal force, and with that, we'll be able to find the threshold. And so for v, let's try to use the conservation of energy here, since the loop is frictionless. So let's try to do that. So for one single bead, we have half mv squared equals to mg delta h. And what is delta h? Well, delta h, so again, let me just draw a diagram here so it's easier to visualize it. So we have, you have a loop here. Let's say it's already here, and now it's here. Remember that this is r, this is also r, this is theta. And the change in height is just this delta h here. And so this is equals to half mv squared equals to mg r. So r is this bigger one and this smaller one. Using trigonometry, this is theta. This should just be r cosine theta. And so delta h is r minus r cosine theta. And so this is the conservation of energy. And so v squared is 2g r minus r cosine theta. And plugging this back into the expression, we get 2mg r minus r cosine theta over r equals to n plus g cosine theta. And then this r, we can cancel it out, so we have 2mg 1 minus cosine theta, so cancel it, equals to n plus this g would just be small mg cosine theta. And so now we get the expression for the normal force, which is n equals to 2mg minus 3mg cosine theta. Rearranging a bit, we get n equals to mg 2 minus 3 cosine theta. So this is the normal force that a single bead experiences. And so this, by Newton's third law, is also the forces that the hoop experiences. This is the reactive force. So if you look at the hoop will experience two such forces, two such normal forces, since you have two beads. So 2n, right? So n and n. And so then we're trying to find the component, the y component of 1n. So how can we do that? So we said that this is theta. And so then by that thing, we have two parallel lines, and that is theta. And then if we look at that, we have 180. So let me just draw again. This is 90 degrees. This whole thing is 180 minus theta. And then this is 90 degrees. To get that, we do 180 minus theta minus 90. We get 90 minus theta. And if this is 90 minus theta, this is 90 degrees, this must be theta. And so ny, the y component of the normal force, must be n cosine theta. And so plugging that in, we get ny equals to mg, 2 minus 3 cosine theta, cosine theta. And so now we have 2ny is smaller or equals to big mg. And so 2 mg, 2 minus 3 cosine theta is smaller than mg. And keep in mind here, we're trying to find the maximum small m over big M, but yet we have another variable here. So what can we do? Well, to ensure that this ratio is definitely the maximum, so to ensure that this, no matter what m is, as long as this ratio is smaller than that, this hoop will never fly off. So in order to do that, we must maximize all other variables, if that makes sense. We must ensure all other variables will not interfere. So let's try to maximize this expression with respect to theta, such that we know for sure that whatever the theta is, this ratio is always the maximum and always correct, and the hoop will never fly off the ground. And so how can we do that? Well, let's differentiate this with respect to theta. So let's call this dFy d theta. So let's call it this the net force in the y direction. And so dFy d theta equals to d theta of, let me just expand this bracket really quickly. Six mg cosine squared theta. And so to do that, let's try to do it. So negative 4 mg sine theta, and the chain rule here, minus 12 mg cosine theta, negative sine theta. I'm just going to change that negative sign to a positive sign. And in order to find the maximum, we need to set the derivative to 0. And then we have 12 mg cosine theta, sine theta, equals to 4 mg sine theta. Sine theta cancels out, mg cancels out, 4 cancels out to 1, this becomes 3. So then we have 3 cosine theta equals to 1, and so cosine theta is equals to 1 over 3, and so theta, critical, is inverse cosine of 1 over 3. This is the critical angle when Fy, the upward force, is maximum. And using that, we can get the expression, and we can be sure that that is the maximum. So let's plug it back in. So remember we said that 2 mg, 2 minus 3 cosine theta must be smaller or equal to big mg. Plug this back into here. We have 2 mg, 2 minus 1 cosine theta, this being 1 over 3, is smaller than bigger mg. And so this becomes 4 mg minus 2 mg over 3. This becomes 2 over 3. Mg must be smaller or equal to big mg. And so then we know, cancel out g. 2 over 3 small m must be smaller or equal to big M. And so m over big M must be smaller or equals to 3 over 2. And that is the maximum ratio for which your hoop will never fly off the ground. Thank you for watching.